Swayam Prabha. Digital India. Educated India.
For the kind invitation and for their students and the team for making our stay here wonderful. And I will join others by paying my deepest and sincere respects to Professor Satyamurthy. He has been a guiding force for many theoretical chemists in India, and he is very sophisticated and suave. I don't know whether I'm pronouncing that word right, but I understand its meaning. Very nice person, gentleman, and a lot of things I've learned from him, and a lot more things to learn from him. In particular, I recommend particularly youngsters to read many of his non-chemistry articles in Current Science. In 2002, if I remember right, sir, he wrote an article in Current Science on 4-year undergraduate program in chemistry. 2002, much before the ICERs. So many articles like that in Current Science over the last few decades. So thank you very much, sir. So I will start on this this talk. There are other things that are going on in my group, so let me spend a minute describing them. We have been working a lot on gas and liquid adsorption in porous matter since 2011, both in collaboration with Professor Tapas Maji, my colleague, as well as on our own. An advertisement spiel is we even have a paper, I even have a paper with this year's Chemistry Nobel Prize winner, Professor Kitagawa, in 2016 in Chemistry European Journal. Where we do both ab initio molecular dynamics simulations, grand canonical Monte Carlo simulations, as well as to calculate adsorption isotomes, as well as recently atmospheric water harvest, using a flat histogram method called the NVT plus W. We have also been interested in developing force fields for modeling molecular liquids. When I use the generic word force field, this force field could be empirical force field, much like what Dr. Swati was mentioning in the previous talk, but also in the recent 3 to 4 years or so, we have been working a lot on machine learned potentials. My current postdoc and former student, Dr. Nikhil, explained it well probably in an aqueous electrolytes poster a couple of days ago. So that brings me to this topic, aqueous electrolytes. Supramolecular systems and dye interactions, the chromophore interactions on surfaces is something we have been interested in. Polymerization, for instance, and how solvent effects can change, how if you change the chain length of the solvent and simple alkane solvent, you can have an aggregate going from H to J. So this is, and many other things. In fact, this month alone, we have 2 ANGU communications coming up. This area has stopped, but we used to work a lot on hybrid biomatter. We've also been working on the formation of intermediate range order in supercooled liquids or inorganic oxide glasses. So that's a kind of that's a broad overview of what we have been working on. But for today, I'll be focusing on ethylene glycol and its aqueous solution, in particular conformer selection, liquid vapor interface. This I may not be able to have time to talk about this, and conformer population versus temperature. This work was primarily carried out by my former graduate student Anjali Gaur, who is now in Paris in Sorbonne University as a postdoc, and one of our recent work was published along with Nikhil, who is in the audience. So ethylene glycol is a small molecule. It's a diol. It's 1,2-ethane diol, right? And you have 2 hydroxyl groups. Oops, sorry, which one? Up is down, down is up. Okay. So there is a single bond here. So you would, and then there are 2 hydroxyl groups. So one would naively expect that the ground state geometry of this molecule would be a trans one for this carbon-carbon bond. But however, due to hyperconjugation, what's called the Gauss effect, the ground state geometry is the Gauss one, okay, and that's what it that's a molecular form, that's a molecular conformation that exists in the crystalline state as well as in gas phase. Whether you do experiments or whether you do theory, that's the geometric ground state. Okay, so in gas phase, it's in Gauss form. When I say Gauss, it's the central carbon-carbon bond that I'm interested in. Okay, but this molecule has 3 torsions. There are 2 CO torsions, the terminal ones, and there is a CC torsion. The CC torsion is the most important one, which determines whether the molecule will have a dipole moment or not. Okay. So both in the gas phase and in the crystalline phase, the molecule is in Gauss form. Okay, but so one would naively expect that the liquid phase also to have Gauss conformer, but that's not true. Although I did talk about only Gauss and trans, there are formally 10 different conformers for this molecule. All of them are listed here depending on the state, conformational state of the terminal dihedral as well as the central dihedral. You can have 10 different conformer populations, and 2 of them have intramolecular hydrogen bond, as you can see here, the one between this and this, and the one between this and this. Okay, and when the central dihedral is the trans conformation, as in here, okay, you can see that the molecule has a center of inversion, okay, and the exclusion principle would apply. The IR active mode will be Raman inactive and so on. Okay, so I want you to realize that. I keep saying this formula: up is down, down is up. Okay, ignore that because that's the way this pointer works. Way back in 1966, Krishnan and Krishnan published a paper in our academy journal on liquid ethylene glycol's Raman spectrum, and their liquid ethylene glycol. Okay, and they were the first people to report this. Okay, 2 strong polarized Raman lines of the liquid which have no corresponding IR absorption bands. Okay, so that means the exclusion principle is operational now. Okay, and which disappear on solidification, which is important. These lines disappear on solidification, have been attributed to the trans conformation of the glycol molecule. Okay, so that's an interesting observation. So this means the conformer which is absent in the gas and in the liquid phase comes into being in the liquid state. Okay, in the gas and the crystalline phase, that's absent, that comes into being in the liquid phase, that's a trans conformer, where the central carbon-carbon bond is in the trans conformation. Okay, so so that was the first observation, and later on people did NMR and they tried to figure out the fraction of the molecules in the trans state, and they found it's about 14%, 100 minus 86, it's about 14% with NMR. Okay, and in any of these things, you have to do a lot of modeling to figure out what the exact, to do the quantitative determination of the fraction. Professor Vasudevan from IPC and his PhD student Aman Jindal did quite a lot of work in this area in the late 2018, just before COVID and just after COVID time. Okay, so they did 2 things. One is they did quite clean spectroscopy, vibrational spectroscopy, infrared and Raman, as well as they did ab initio molecular dynamics simulation. Okay, one trajectory of liquid ethylene glycol 50 picosecond log using this DFT with CPMD, plane wave basis set code. Okay, so you can see here that this particular green color band that is active, this is Raman and this is IR absorption, and you see this green color, this particular green color band is present in Raman but is absent in the IR. Okay, so that's the clear signature of the presence of trans conformation, and they using this DFT level of theory, they determined the fraction of trans conformers to be 22%. Okay, so 22% trans, 78% gauche. Okay, so that was their determination. I happen to have reviewed a couple of their papers for the journal, as well as I happen to be the thesis examiner for Aman Jindal's PhD thesis. Okay, and I'm honest admission, the work was very good, appeared very clean, but I was a little doubtful if this 22% that was there in the ab initio simulations was because of the insufficient sampling and whether initial configuration effects were present in the during in the simulation itself, because the trajectory length is only 50 picosecond. Okay, so I asked these questions to Aman during his PhD thesis, and he answered them very well. Okay, so he was awarded the PhD degree, and he is now becoming in this later this month he is becoming an Inspire faculty fellow, and he is coming to my lab after his postdoc. Okay. Another thing, another piece of information, I'll come back to the story again. I want to tell the background to this ethylene glycol. Chris Kramer, whom somebody mentioned, here. And Don Truller published a paper, JAX, in '94 on very accurate implicit solvent calculations, quantum chemical calculations of both ethylene glycol in gas phase as well as in implicit water. Okay, and listing out, calculating the free energies of all these 10 conformers that I showed you. Okay, and then free energies of them, and then they could figure out what the population should be in water. Okay, so in gas phase they got 2% trans. Okay, 2% to be in the trans conformation, and in the implicit water they got 88% to be in the gauche, that is 12%. Okay, the 2% in gas becomes 12% in water. Okay, so this was their calculation. Okay, now I've told you two independent pieces of information: ab initio MD simulation of the liquid phase by Vasudevan and Jindal, 22% trans, 2% trans in gas phase, Kramer and Truller, 12% trans in implicit water. Okay. So these are three numbers. Okay, remember that. So I told you about my doubts on the CPMD trajectory being small. The important reason I wanted to tell you is liquid water is 1 centipoise viscosity, whereas liquid ethylene glycol is 16 centipoise viscosity. So the relaxation times to sample different conformations would be much larger in ethylene glycol than what will be there in water with its large, very high diffusivity and low viscosity. So that was the that was bothering me. So I asked Anjali to, as part of her thesis, to start working on reproducing that calculation, and they were correct. Okay, Jindal and Vasudevan were correct. We of course did a slightly different DFT level of theory, PBD3, and we used CP2K, the mixed base set code, and we did we did two independent runs. We started from two independent different initial configurations. Okay, with different populations of trans, one having about 24% trans, and another having about 12 to 15% trans, and both of them converge to the same value as what Jindal and Vasudevan predicted. Okay, 21-22% of that order. Okay, in liquid ethylene glycol at ambient condition. I had one remark in the Jindal Vasudevan slide that no force field in the literature was able to reproduce this 21-22%. Okay. Okay, sorry. Yeah. Yeah, so okay. So no force field in the, oops, sorry. No force field in the literature provides accurate conformer populations. And I'm correcting it. No force field in the literature used to provide accurate conformer populations. Okay, the previous slide was an old one, and after we published, I am claiming that ours is the only one that provides. So we did accurate dihedral refinement, potential refinement, and we had to tune the Lennard-Jones parameters, and we have two versions of the force field. One is called FFV1 and FFV2, and our force field reproduces the torsional populations quite accurately. Okay, of in the liquid phase. So this is these are torsional distributions of the central torsion from every known potential until ours came. Okay, you can see all sorts of, including cis. All these are published results, both off-the-shelf commodity force fields as well as force fields that have been that appear to have been tuned specifically for liquid ethylene glycol. Okay. Primarily because nobody knew what the correct value was of the torsion, and you could get accurate, quantitatively accurate physical properties with wrong torsional populations. Unfortunate truth, but it is true. Okay. But it's hard one that needs to be said. So the summary is here. AMD simulations 21%, our force fields give either 21, 23% or so. Okay. We could also reproduce the, we could also obtain the free energy from using metadynamic simulations in the liquid phase, the free energy profile of this particular torsion, and the free energy difference between the trans and the gauche forms is about 2 kilojoule per mole. Okay, favoring the gauche, of course. Physical properties are on the money. Density as a function of temperature, diffusion coefficients on the money, and viscosity quite good. And so you have heat of vaporization numbers. The deviation from experiment is about 3%. Surface tension deviation is about 7%. Dielectric constant, which Professor Susanto gave a nice talk on time correlation function, the Heisenberg picture, and little bit touching upon maybe a Green-Kubo linear response and so on. Okay, so these are Green-Kubo calculations for the dielectric constant, the moment time correlation function integral, and experiment is 41, simulation is 26, 27. Okay, so you have quite a bit of a deviation of about 30% under prediction in dielectric constant, but everything else right on the money quantitatively. And I'm going to delve, the rest of my talk is going to talk about the deviation in the dielectric constant. So if you look at the dipole moment distribution, we can obtain the molecular dipole moment distributions, and from ab initio molecular, remember we did 2 ab initio molecular dynamic simulations, okay, and from the localization of the Vanier functions, we can localize them to obtain Vanier centers, and using these Vanier centers as centers of electrons, okay, the electronic charge and the nuclear charge, we can assign a dipole moment for each molecule, individual molecule, and obtain that distribution. That is the blue curve. You can take that as the ground truth for now. I'm going to change the ground truth later. Our force fields give this green and this red curve, okay, and not bad. And so another variant of the dipole moment calculation gives this black curve. And the dielectric constant is about 30 with the other force field, and so we have a deviation of about 30% or so from the experimental value, and this deviation in the dielectric constant we believe is because of the under prediction of the molecular dipole moment in the simulation, okay, with the force field through the Debye-Onsager relation, which says that the dielectric constant is related to the square, is proportional to the square of the molecular dipole moment. Okay, And so there is scope for improvement, which if you can include the polarizability to match the ab initio molecular dynamics dipole moment distribution. So another detail is that there are two large peaks, two prominent peaks in this distribution. This one, the low dipole moment one, is coming largely from trans conformers, and the high dipole moment is coming largely from gauche conformers. Okay, and the mean dipole moment is about between 3 to 4 dBi or so. Suppose, can I reproduce the Kramer and Truller result done with accurate quantum mechanics using either my force field or using ab initio MD? Okay, the answer is yes. So I am going to dilute ethylene glycol with water. I do an ab initio MD simulations. Although this is very expensive, we still have not published this particular figure, by the way. You see here two different ab initio MD runs. 5 mole% of ethylene glycol in water, and we start from 50% trans, and another run with 0% trans. Both of them converge to the same value, about 11 to 12%, which is what the Kramer and Truller result with the implicit model was. So we are confirming Kramer and Truller, who did implicit solvent calculations with ab initio MD simulations of the liquid phase. Now the surprising result is that this is found to be true. You don't even need electronic degrees of freedom. Our force field is able to reproduce that. Okay, so this is the conformer population distribution. Okay, as a function of the dilution, you have fully ethylene glycol. Sorry, I'm getting a little cataract, so I'm not able to identify my colors. Probably this is green. So this is fully ethylene glycol, and this is dilute ethylene glycol solution. And as you dilute it, the trans population has to decrease. Okay, so this is the trans region, and this is the gauche population. Okay, the trans peak decreases from about 22% to about 12%. You see here, this is the trans population starts from about 21% to about close to 12. We don't get 12 because we have the lowest mole fraction we can go to is 5. Okay, because otherwise the system size becomes very large. So you see a neat reduction in the trans population upon dilution. This is not far-fetched to understand. You are taking ethylene glycol from a liquid ethylene glycol, which is having a dielectric constant of about 40, and putting it into a polar solution, which is water, having a dielectric constant of 80. So the new solvent is going to prefer the solute, which is ethylene glycol, to be in a more polar conformation than in a less polar conformation. So the gauche is more polar conformation. The trans is a zero dipole moment conformation. So the gauche conformer population increases, or the trans one decreases. Okay, so that, and we get this quantitatively right. So the population of trans conformers monotonically decreases upon dilution in response to the increasing polarity of the solution. Now we have heard many talks in this meeting on machine learned potentials. So we were interested in developing a machine learned potential for ethylene glycol to model its liquid state as well as any state for that matter, and the rest of the story is on that. I'll probably skip the details of the MLP. You can look up the papers, but we use DPMD, okay, DPMD kit for the development of the MLP. We also have in our group quite a bit of experience with working with MACE as well. Okay, we rarely use foundation models because they are too heavy, so we develop our own MLP specific for specific substances. So I will skip these introductory slides for a lack of time. I will talk about this particular work, okay, which is on the temperature dependent conformer populations and dipole moment distributions in ethylene glycol, which appeared in JCTC this year. So we have the same split up that many many including Dilip talked about, the training, validation, and the test. So 80-20, 80-10-10, or 70-10-20, like that. Okay, that kind of split. And we use DPMD, which comes with a we do an active learning procedure to develop this MLP. In this particular ethylene glycol case, we had 23 generations, after which we got stable, reliable trajectories. Remember that we need to span over the entire liquid range of ethylene glycol, which spans from about 260 Kelvin, which is the freezing point, to about 460 Kelvin. So a temperature range of 200 Kelvin. So because of which we require quite many generations of active learning. And so 23 generations of active learning with either 40 to 150 ethylene glycol molecules, with a total of about 23,000 configurations were involved in this. And these are done. The training set consisted of either AI ab initio MD simulations as well as classical MD simulations with reduced bond or angle force constants, and 6 angstrom in the cutoff in the embedding network. And the ground truth is DFT at RIPP-D3 level with 1200 read bar cutoff for electron density. Time step is half a femtosecond, and these are our RMSEs. Energy RMS is half a MeV per atom, and force RMS is about 60 MeV per angstrom. Apart from developing a MLP, a deep potential model for the interatomic potential, we also have a deep Vanier model that will give you the molecular dipole moment based on the atomic molecular configurations, okay, in the liquid. So we developed that as well, a deep Vanier model, so that we can obtain the dipole moment of molecules. So with this MLP, we were able to simulate the crystal, and this is, remember, the crystal is not at 0 Kelvin, the crystal is at ambient conditions. Okay, so 1 atmosphere pressure, whatever I think 230 Kelvin or something is when the crystal structure was determined. We could reproduce the lattice constants. The experiment is this. DPMD is the deep potential molecular dynamics. Liquid density as a function of temperature, okay, over a wide range of temperature. All the DPMD simulations are done with 500 ethylene glycol molecules. Pretty large box, well converged results, several tens of nanosecond trajectories and so on. We could get the self-diffusion coefficient quite well. We are also able to reproduce the both the intramolecular hydrogen bond as well as the intermolecular hydrogen bond distributions. One may ask, why is DPMD required when ab initio molecular dynamics is worked? Okay, ab initio, I told you that I'm going to change that ground truth, and this is that moment. You see, look at the conformational distribution of the central dihedral angle from ab initio MD, which is blue color, green is classical, and DPMD is red. All of them match. Whereas if you look at the terminal torsions, this is a symmetric molecule, so the terminal torsional distributions should be symmetric, okay, on either side of 0 degree. But you see here, the ab initio MD simulation, one of the terminal torsions is this blue curve, the other is this orange curve. They are asymmetric, okay, and that asymmetry is because of the length of the trajectory is not sufficiently large in the ab initio MD simulation for you to have sampled both the torsions adequately. So one should not be complacent in thinking that, yeah, I have got the big iron, I have the ab initio MD simulation, everything that I do is correct and fine. No, you got to check, particularly the sampling part. And if you use DPMD, then you get very symmetric distributions. So the conformer population, what happens is the trans population starts from about 21, and the DPMD prediction is that it goes up to 24%, very close to the gas phase, very close to boiling point. Okay, it goes to about 24%, and that can be explained as the fact that the trans is higher in potential energy, so you will have more population in trans as with increasing temperature. However, the molecules are also moving farther apart because of the increase in the volume of the sample, which favors the gauche. So there are two competing effects. One is that the trans is higher in energy, so with increasing temperature, the population should be increasing. The competing effect is the gauche population is also increasing because the intermolecular distances are increasing and the molecules are feeling more in a gas phase like environment than in the condensed liquid phase. Okay. The chair mentioned that I'm nearly out of time, so I'll skip the results on the intermolecular distance distribution. And I told you about the molecular dipole moment distribution. We get this right. This is the exact dipole moment distribution is obtained from this red curve, which is not coinciding with the ab initio MD simulation. We believe that the red curve is the true dipole moment distribution, not the ab initio MD one, which is because of the lack of sampling in the ab initio MD. And the mean dipole moment is about 3.3 dBi, okay, at ambient condition. Okay, so this is the correct mean dipole moment of ethylene glycol molecule in liquid ethylene glycol. And this difference, this 3.3 dBi versus the about 2.9 dBi that we got in force field, it explains the deviation in the dielectric constant being 30 instead of 40. Okay. With that, let me summarize. We have studied liquid ethylene glycol with the force field, with ab initio MD simulations, as well as with a machine learned potential, and we got pretty good molecular dipole moment distributions, which I believe is the ground truth for as far as the liquid state is concerned. I want to close by a thought. Ethylene glycol, the dielectric constant decreases with increasing temperature pretty much for every liquid, right? Is there a contra example? Answer is yes. For many liquids, you can have dielectric constant increase in temperature. I'm showing you some experimental data for dimethyl carbonate. It shows a marginal increase with increasing temperature, and that's because the population of a conformer with a higher dipole moment, it is the lower energy state, and that population increases with increasing temperature. So these are pretty neat examples of how molecular conformations, dipole moment, dielectric constant, and temperature play a role in determining the liquid properties. Thank you for your attention.
Swayam Prabha, Digital India, Educated India.